I'll see you in the next video. Let's write some visualization code. Let's now follow our Data Explorer's motto of visualizing our transformed images. So we saw what it looks like to pass one image through a data transform. And if we wanted to find more documentation on Torch Vision transforms, where could we go? There's a lot of these. So transforming and augmenting images. This is actually going to be your extra curriculum for this video. So transforms are common image transformations available in the transforms module. They can be chained together using compose, which is what we've already done. Beautiful. And so if you'd like to go through all of these, there's a whole bunch of different transforms that you can do, including some data augmentation transforms. And then if you'd like to see them visually, I encourage you to check out illustration of transforms. But let's write some code to explore our own transform visually first. So I'll leave this as a link. So I'll go up here, right here. Transforms help you get your images ready to be used with a model / perform data augmentation. Wonderful. So we've got a way to turn images into tensors. That's what we want for our model. We want our images as PyTorch tensors. The same goes for any other data type that you're working with. But now I'd just like to visualize what it looks like if we plot a number of transformed images. So we're going to make a function here that takes in some image paths, a transform, a number of images to transform at a time, and a random seed here because we're going to harness the power of randomness, and sometimes we want to set the seed, sometimes we don't. So we have an image path list that we've created before, which is just all of the image paths that we have of our data set. So data, pizza, steak, sushi. Now, how about we select some random image paths and then take the image from that path, run it through our data transform, and then compare the original image of what it looks like and the transformed image and what that looks like. Let's give it a try, hey? So I'm going to write a docstring of what this does, and then selects random images from a path of images and loads / transforms them, then plots the original versus the transformed version. So that's quite a long docstring, but that'll be enough. We can put in some stuff for the image paths, transforms, and seed. We'll just code this out. Let's go random seed. We'll create the seed. Maybe we do it if seed, random seed. Let's put that. And we'll set seed to equal none by default. That way we can, we'll see if this works, hey? If in doubt, code it out. Random image paths, and then we're going to go random sample from the image paths and the number of sample that we're going to do. So random sample is going to, this will be a list. I'll just pass in here that this is a list. So we're going to randomly sample k, which is going to be n, so 3 images from our image path list. And then we're going to go for image path. We're going to loop through the randomly sampled image paths. You know how much I love harnessing the power of randomness for visualization. So for image path in random image paths, let's open up that image using pill. Image.open image path as f. And then we're going to create a figure and an axis. And we're going to create a subplot with matplotlib. So subplots. And we want it to create one row. So it goes n rows, n cols. One row and n cols equals 2. And then on the first, or the 0th axis, we're going to plot the original image. So imshow, we're just going to pass it straight in f. And then if we want to go ax 0, we're going to set the title. So set title, we're going to set it to be the original. So we'll create this as an f string, original, and then new line, we'll create a size variable. And this is going to be f.size. So we're just getting the size attribute from our file. So we'll keep going and we'll turn off the axes here. So axis, and we're going to set that to false. Now let's transform on the first axis plot. We're going to transform and plot target image. This is so that our images are going to be side by side, the original and the transformed version. So there's one thing that we're going to have to do. I'll code it out in the wrong way first. I think that'll be a good way to illustrate what's going on. F. So I'm just going to put a note here. Note, we will need to change shape for matplotlib because we're going to come back here. Because what does this do? What have we noticed that our transform does? If we check the shape here, oh, excuse me, it converts our image to color channels first. Whereas matplotlib prefers color channels last. So just keep that in mind when we're going forward. This code, I'm writing it, it will error on purpose. So transformed image, and then we're going to go ax1 as well. We're going to set the title, which is going to be transformed. And then we'll create a new line and we'll say size is going to be transformed image.shape. Oh, probably better. Yeah, we could probably go shape here. And then finally, we're going to go ax1. We're going to turn the axis. We're going to set that to false. You can also set it to off. So you could write false or you could write off. You might see that, different versions of that somewhere. And I'm going to write a super title here, which we'll see what this looks like. Class is going to be image path. So we're getting the target image path, and we're just going to get the attribute or the parent attribute and then the stem attribute from that, just like we did before to get the class name. And then I'm going to set this to a larger font size so that we make some nice looking plots, right? If we're going to visualize our data, we might as well make our plots visually appealing. So let's plot some transformed data or transformed images. So image paths, we're going to set this to image path list, which is just the variable we have down below, which is a path list, a list containing all of our image paths. our transform. We're going to set our transform to be equal to our data transform. So this just means that if we pass the transform in, our image is going to go through that transform and then go through all of these. It's going to be resized, it's going to be randomly horizontally flipped, and it's going to be converted to a tensor. And then, so we're going to set that data transfer there, or data transform, sorry. N is going to be 3, so we plot 3 images, and we'll set the seed to 42 to begin with. Let's see if this works. Oh, what did we get wrong? We have invalid shape. The train whole 1 and 2, so up in from here, and sushi data. So I've file. How about we write here? So with read image. So and now I'm here that represents the images now is in numerical format. Wonderful. So okay, available in the transforms modules. There's a go here, permute. This is what we have to do. We have to permute. We have to swap the order of the axes. So right now our color channels is let's go here, permute. This is what we have to do. We have to permute. We have to swap the order of the axes. So right now our color channels is first. So we have to bring this color channel axis or dimension to the end. So we need to shuffle these across. So 64 into here, 64 into here, and 3 on the end. We need to, in other words, turn it from color channels first to color channels last. So we can do that by permuting it to have the first axis come now in the 0 dimension spot, and then number 2 is going to be in the first dimension spot, and then number 0 is going to be at the back end. So this is essentially going from C, H, W, and we're just changing the order to be HWC. So the exact same data is going to be within that tensor, we're just changing the order of the dimensions. Let's see if this works. Woohoo, look at that. Oh, I love seeing some manipulated data. We have a class of pizza, and the original image is there, and it's 512 by 512, but then we've resized it using our transform. Notice that it's a lot more pixelated now, but that makes sense because it's only 64 pixels. Now, why might we do such a thing? Well, one, does this image still look like that? Well, to me, it still does, but the most important thing will be, does it look like that to our model? Does it still look like the original to our model? Now, 64 by 64, there is less information encoded in this image. So our model will be able to compute faster on images of this size. However, we may lose some performance because not as much information is encoded as the original image. Again, the size of an image is something that you can control. You can set it to be a hyperparameter. You can tune the size to see if it improves your model. But I've just decided to go 64:3 in line with the CNN Explainer website. So a little hint, we're going to be re-replicating this model that we've done before. Now you notice that our images are now the same size, 64:3, as what the CNN Explainer model uses. So that's where I got that from. But again, you can change this to size to whatever you want. And we see, oh, we've got a steak image here, and you notice that our image has been flipped on the horizontal. So the horizontal axis, our image has just been flipped, same with this one here. So this is the power of torch transforms. Now there are a lot more transforms, as I said. You can go through them here to have a look at what's going on. Illustrations of transforms is a great place. So there's resize, there's center crop, you can crop your images, you can crop 5 different locations, you can do grayscale, you can change the color, a whole bunch of different things. I'd encourage you to check this out. That's your extra curriculum for this video. But now that we've visualized the transform, this is what I hinted at before, that we're going to use this transform for when we load all of our images into a torch dataset. So I just wanted to make sure that they had been visualized first. We're going to use our data transform in the next video when we load all of our data using a torchvision.datasets helper function. So let's give that a go. I'll see you in the next video. Have a look at that beautiful plot. We've got some original images and some transformed images. And the beautiful thing about our transformed images is that they're in tensor format, which is what we need for our model. That's what we've been slowly working towards. We've got a data set, and now we've got a way to turn it into tensors, ready for a model. So let's just visualize I'll turn the seed off here so we can look at some more random images. There we go. Okay, so we've got steak, pixelated because we're downsizing 64:3. Same thing for this one, and it's been flipped on the horizontal. And then same thing for this pizza image, and we'll do one more to finish off. Wonderful. So that is the premise of transforms, turning our images into tensors, and also manipulating those images if we want to. So let's get rid of this. I'm going to make another heading. We're up to part 4 now, and this is going to be option 1. So loading image data using image folder. And now I'm going to turn that into Markdown. And so let's go Torch Vision datasets. So recall how each one of the Torch Vision domain libraries has its own datasets module that has built-in functions for helping you load data. In this case, we have an image folder, and there's a few others here if you'd like to look into those. But an image folder, this class is going to help us load in data that is in this format, the generic image classification format. So this is a pre-built datasets function. Just like there's pre-built datasets, we can use pre-built dataset functions. Now, option 2 later on, this is a spoiler, is we're going to create our own custom version of a dataset loader, but we'll see that in a later video. So let's see how we can use image folder to load all of our custom data, our custom images, into tensors. So this is where the transform is going to come in helpful. So let's write here, we can load image classification data using, let's write this, let's write the full path name, torchvision.datasets.image folder. Put that in there. Beautiful. And so let's just start it out. Use image folder to create datasets. And now in a previous video, I hinted at the fact that we can pass a transform to our image folder class. That's going to be right here. So let's see what that looks like in practice. So from Torch Vision, I'm going to import datasets because that's where the image folder module lives. And then we can go train data equals datasets.image folder. And we're going to pass in the root, which is our train dir, because we're going to do it for the training directory first. And then we're going to pass in a transform, which is going to be equal to our data transform. And then we're going to pass in a target transform, but we're going to leave this as none, which is the default, I believe. If we go up to here, yeah, target transform is optional. So what this means is this is going to be a transform for the data, and this is going to be a transform for the label / target. PyTorch likes to use target, I like to use label, but that's okay. So this means that we don't need a target transform because our labels are going to be inferred by the target directory where the images live. So our pizza images are in this directory and they're going to have pizza as the label because our data set is in standard image classification format. Now, if your data set wasn't in standard image classification format, you might use a different data loader here. A lot of them will have a transform for the data. So this transform is going to run our images, whatever images are loaded from these folders, through this transform that we've created here. It's going to resize them, randomly flip them on the horizontal, and then turn them into tensors, which is exactly how we want them for our PyTorch models. And if we wanted to transform the labels in some way, shape, or form, we could pass in a target transform here. But in our case, we don't need to transform the labels. So let's now do the same thing for the test data. And so that's why I wanted to visualize our transforms in the previous videos, because otherwise we're just passing them in as a transform. So really what's going to happen behind the scenes is all of our images are going to go through these steps. And so that's what they're going to look like when we turn them into a data set. So let's create the tester here, or the test data set. The transform, we're going to transform the test data set in the same way we've transformed our training data set. And we're just going to leave that like that. So let's now print out what our data sets look like. Train data and test data. Beautiful. So we have a data set, a torch data set, which is an image folder, and we have a number of data points. This is going to be for the training data set. We have 225, so that means about 75 images per class. And we have the root location, which is the folder we've loaded them in from, which is our training directory. We've set these two up before, traindir and testdir. And then we have a transform here, which is a standard transform, a resize, followed by a random horizontal flip, followed by 2tensor. Then we've got basically the same output here for our test directory, except we have less samples there. So let's get a few little attributes from the image folder. This is one of the benefits of using a PyTorch pre-built data loader, or dataset loader, is that it comes with a fair few attributes. So we could go to the documentation, find this out from in here, inherits from dataset folder, keep digging into there, or we could just come straight into Google Colab. Let's go get class names as a list. Can we go train data dot and then press tab? Beautiful. So we've got a fair few things here that are attributes. Train data dot and then press tab. Beautiful. Let's have a look at classes. This is going to give us a list of the class names. This is very helpful later on. So we've got pizza, steak, sushi. We're trying to do everything with code here. So if we have this attribute of traindata.classes, we can use this list later on for when we plot images straight from our dataset or make predictions on them and we want to label them. You can also get class names as a dictionary mapped to their integer index, that is. So we can go train data dot and press tab. We've got class to IDX. Let's see what this looks like. Class dict. Wonderful. So then we've got our string class names mapped to their integer. So we've got pizza is 0, steak is 1, sushi is 2. Now, this is where the target transform would come into play. If you wanted to transform these labels here in some way, shape, or form, you could pass a transform into here. And then if we keep going, let's check the lengths of what's going on. Check the lengths of our data set. So we've seen this before, but this is going to just give us how many samples that we have. Length, train data, length, test data. Beautiful. And then, of course, if you'd like to explore more attributes, you can go train data dot, and then we've got a few other things, functions, images, loader, samples, targets. If you wanted to just see the images, you can go dot samples. If you wanted to see just the labels, you can go dot targets. This is going to be all of our labels. Look at that. And I believe they're going to be in order. So we're going to have 0, 0, 0, 1, 1, 1, 2, 2, 2. And then if we wanted to have a look, let's say we have a look at the first sample, hey? We have data, pizza, steak, sushi, train, pizza. There's the image path, and it's a label 0 for pizza. Wonderful. So now we've done that, how about we've been visualizing this whole time. So let's keep up that trend, and let's visualize a sample and a label from the train data dataset. So in this video, we've used image folder to load our images into tensors. And because our data is already in standard image classification format, we can use one of TorchVision.dataset's pre-built functions. So let's do some more visualization in the next video. I'll see you there. Welcome back. In the last video, we used datasets.imagefolder to turn all of our image data into tensors. And we did that with the help of our data transform, which is a little pipeline up here to take in some data, or specifically an image, resize it to a value that we've set, in our case 6464, randomly flip it along the horizontal. We don't necessarily need this, but I've just put that in there to indicate what happens when you pass an image through a transforms pipeline. And then, most importantly, we've turned our images into a torch tensor. So that means that our data, our custom data set, this is so exciting, is now compatible to be used with a PyTorch model. So let's keep pushing forward. We're not finished yet. We're going to visualize some samples from the train data dataset. So how can we do this? We can index on the train data dataset to get a single image and a label. So if we go, can we do train data 0? What does that give us? Okay, so this is going to give us an image tensor and its associated label. In this case, it's an image of pizza, because why? Its associated label is pizza. So let's take the 0th 0. So this is going to be our image, and the label is going to be train data 0, and we're just going to get the first index item there, which is going to be 1. And then if we have a look at them separately, image and label, Beautiful. So now one of our target images is in tensor format, exactly how we want it, and its label is in numeric format as well, which is also exactly how we want it. And then if we wanted to convert this back to a non-label, we can go class names. Now one of our target images is in tensor format, exactly how we want it, and its label is in numeric format as well, which is also exactly one. And then if we have a look at them separately, image and label. Beautiful. So now one of our target images is in tensor format, exactly how we want it, and its label is in numeric format as well, which is also exactly how we want it. And then if we wanted to convert this back to a non-label, we can go class names and index on that, and we see pizza. And I mean, non-label is in non-numeric. We can get it back to string format, which is human understandable. We can just index on class names. So let's print out some information about what's going on here. Print F, we're going to go image tensor. I love F strings if you haven't noticed yet. Image tensor, and we're going to set in new line. We're going to pass it in our image, which is just the image that we've got here. Then we'll print in some more information about that. This is still all becoming one with the data, right? We're slowly finding out information about our data set so that if errors arise later on, we can go, our image, or we're getting a shape error, and I know our images are of this shape, or we're getting a data type error, which is why I've got the .d type here, and that might be why we're getting a data type issue. So let's do one more with the image label. Oh, well, actually, we'll do one more. We'll do print. We'll get the label data type as well. Label. This will be important to take note of later on. Type. As I said, 3 big issues: shape mismatch, device mismatch, and data type mismatch. Can we get the type of our label? Beautiful. So we've got our image tensor, and we've got its shape. It's of torch size 364/64. That's exactly how we want it. The data type is torch float 32, which is the default data type in PyTorch. Our image label is 0, and the label data type is of integer. So let's try and plot this and see what it looks like, hey, using matplotlib. So first of all, what do we have to do? Well, we have to rearrange the order of dimensions. In other words, matplotlib likes color channels last. So let's see what this looks like. We'll go image permute. We've done this before. Image.permute 1, 2, 0 means we're reordering the dimensions. 0 would usually be here, except that we've taken the 0th dimension, the color channels, and put it on the end and shuffled the other 2 forward. So let's now print out different shapes. I love printing out the change in shapes. It helps me really understand what's going on. Because sometimes I look at a line like this and it doesn't really help me, but if I print out something of what the shapes were originally and what they changed to, well, hey, that's a big help. That's what Jupyter Notebooks are all about, right? So this is going to be color channels first, height, width.
Hey, my name is Gleb Alexandrov, and this is this, and I wonder how familiar that sounds. No matter what I do with, or even some of the boxes from this list, it will instantly improve.
Scientists have discovered the true ferocity of a
has been sculpted and scarred.
We didn't map enough. This volcano even exceeded our maximum expectations of
explosions in history. And the impression left on the seafloor gives a sense of its violent energy. Scientists calculate that some 10 cubic kilometers of material has been displaced, equivalent to the volume of 4,000 Egyptian pyramids. 2/3 of that was the ash and rock ejected out through the volcano's opening, but the other third was material scraped off the sides of the volcano as debris fell back out of the sky and tumbled across the bottom of the ocean.
the plume itself rose 53 kilometers into the atmosphere. I mean, this was truly the most dramatic event in volcanic history since possibly Krakatoa in 1883.
This eruption was extraordinarily powerful, but there are similar volcanoes lurking underwater off coastlines around the world. By understanding what happened
In February 2021, a winter storm that swept through Texas caused one of the most severe power crises in American history. The cold weather created shockingly high electricity demands as people tried to keep their homes warm. But it also caused problems with the power supply because power plants themselves and their supporting infrastructure weren't adequately protected against freezing weather. The result was that Texas couldn't generate enough power to meet demand. Instead, they would have to disconnect customers to reduce demands down to manageable levels. But before grid operators could shed enough load from the system, the frequency of the alternating current dropped as the remaining generators were bogged down, falling below 59.4 Hz for over 4 minutes. It might not seem like much, but that is a critical threshold in grid operations. It's 1% below nominal. Power plants have relays that keep track of grid frequency and disconnect equipment if anything goes awry to prevent serious damage. If the grid frequency drops below 59.4 Hz, the clock starts ticking. And if it doesn't return to the nominal frequency within 9 minutes, the relays trip. That means the Texas grid came within a bathroom break from total collapse. If a few more large power plants tripped offline, or too few customers were shed from the system in time, it's likely that the frequency would have continued to drop until every single generator on the grid was disconnected. Thankfully, that nightmare scenario was avoided. Still, despite operators preventing a total collapse, the 2021 power crisis was one of the most expensive and deadly disasters in Texas history. If those 4 minutes had gone differently, it's almost impossible to imagine how serious the consequences would be. Let's put ourselves in the theoretical boots of someone waking up after that frigid February night in Texas, assuming the grid did collapse, and find out. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the impacts of blackouts on other infrastructure. Every so often, some loud noise wakes you up from your sleep. A truck backfiring on the street outside, a baby crying, a cat knocking something off a shelf. But it's a very
And depending on what data you're using, if you're not using images, if you're using text, still knowing the shape of your data is a very good thing. We're going to go image permute.shape, and this should be, everything going right, is height, width, color channels on the end here. And we're just going to plot the image. Can never get enough plotting practice. Plot the image. We're going to go plt.figure. We'll pass in fig size equals 10.7. And then we're going to go plt.imshow. We'll pass in the permuted image, image underscore permutes, and then we'll turn off the axes, and we will set the title to be class names, and we're going to index on the label just as we did before, and we're going to set the font size equal to 14 so it's nice and big. Here we go. Beautiful. Or And we're going to set the font size equal to 14, so it's nice and big. Here we go. Beautiful. There is our image of pizza. It is very pixelated because we're going from about 512 as the original size, 512 by 512 to 6464. I would encourage you to try this out. Potentially you could use a different image here. So we've indexed on sample 0. Maybe you want to change this to just be a random image and go through these steps here. And then if you'd like to see different transforms, I'd also encourage you to try changing this out, our transform pipeline here. Maybe increase the size and see what it looks like. And if you're feeling really adventurous, you can go into Torch Vision and look at the transforms library here and then try one of these and see what it does to our images. But we're going to keep pushing forward. We are going to look at another way. Or actually, I think for completeness, let's now turn, we've got a data set. We wrote up here before that we wanted to turn our images into a data set and then subsequently a Torch Utils data loader. So we've done this before by batching our images or batching our data that we've been working with. So I'd encourage you to give this a shot yourself. Try to go through the next video and create a train data loader using our train data, wherever that is, train data, and a test data loader using our test data. So give that a shot, and we'll do it together in the next video. We'll turn our data sets into data loaders. Welcome back. How'd you go? In the last video, I issued you the challenge to turn our data sets into data loaders. So let's do that together now. I hope you gave it a shot. That's the best way to practice. So turn loaded images into data loaders. So we're still adhering to our PyTorch workflow here. We've got a custom data set. We found a way to turn it into tensors in the form of data sets, and now we're going to turn it into a data loader so we can turn our data sets into iterables or batchify our data. So let's write down here, a data loader is going to help us turn our data sets into iterables. And we can customize the batch size, write this down, so our model can see batch size images at a time. So this is very important. As we touched on in the last section, computer vision, we create a batch size because if we had 100,000 images, chances are if they were all in one data set, there's 100,000 images in the Food 101 data set, we're only working with about 200. If we tried to load all 100,000 in one hit, chances are our hardware may run out of memory. And so that's why we batchify our images. So if we have a look at this, NVIDIA SMI, our GPU only has 16 gigabytes. I'm using a Tesla T4 right now. Well, it has about 15 gigabytes of memory. So if we try to load 100,000 images into that, whilst also computing on them with a PyTorch model, potentially we're going to run out of memory and run into issues. So instead, we can turn them into a data loader so that our model looks at 32 images at a time and can leverage all of the memory that it has rather than running out of memory. So let's turn our train and test data sets into data loaders. Turn train and test data sets into data loaders. Now, this is not just for image data. This is for all kinds of data in PyTorch. Images, text, audio, you name it. So import data loader. Then we're going to create a train data loader. We're going to set it equal to data loader. We're going to pass in a data set. So let's set this to train data. Let's set the batch size. What should we set the batch size to? I'm going to come up here and set it as a capital variable. I'm going to use 32 because 32 is a good batch size. So we'll go 32. Or actually, let's start small. Let's just start with a batch size of 1 and see what happens. Batch size 1. Number of workers. So this parameter is going to be, this is an important one. I potentially have covered it before, but I'm going to introduce it again. Is this going to be how many cores or how many CPU cores that is used to load your data? So the higher the better usually. And you can set this via OS CPU count, which will count how many CPUs your compute hardware has. So I'll just show you how this works. Import OS, and this is a Python OS module. We can do CPU count to find out how many CPUs our Google Colab instance has. Mine has 2. Your number may vary, but I believe most Colab instances have 2 CPUs. If you're running this on your local machine, you may have more. If you're running it on dedicated deep learning hardware, you may even have even more, right? So generally, if you set this to 1, it will use 1 CPU core, but if you set it to os.cpu count, it will use as many as possible. So we're just going to leave this as 1 right now. You can customize this to however you want. And I'm going to shuffle the training data because I don't want my model to recognize any order in the training data, so I'm going to mix it up. And then I'm going to create the test data loader. Data set equals test data, and batch size equals 1. Num workers, I'm going to set this to equal 1 as well. Again, you can customize each of these. They're hyperparameters to whatever you want. Number of workers, generally the more the better. And then I'm going to set shuffle equals false for the test data so that if we want to evaluate our models later on, our test data set is always in the same order. So now let's have a CPU count. To find out how many CPUs our Google Colab instance has. Mine has 2. Your number may vary, but I believe most Colab instances have 2 CPUs. If you're running this on your local machine, you may have more. If you're running it on dedicated deep learning hardware, you may even have even more, right? So generally, if you set this to 1, it will use 1 CPU core, but if you set it to os.cpu count, it will use as many as possible. So we're just going to leave this as 1 right now. You can customize this to however you want. And I'm going to shuffle the training data because I don't want my model to recognize any order in the training data, so I'm going to mix it up. And then I'm going to create the test data loader, data set, and 2 instances of torchutils.data.dataloader. And now we can see if we can visualize something from the train data loader as well as the test data loader. Or actually, maybe we'll just visualize something from one of them so we're not just double handling everything. Do we get a length here? Wonderful. Because we're using a batch size of 1, our lengths of our data loaders are the same as our data sets. Now, of course, this would change if we set, oh, we didn't even set this to the batch size parameter. Batch size. Let's come down here and do the same here. Batch size. So we'll watch this change. If we wanted to look at 32 images at a time, we definitely could do that. So now we have 8 batches because 225 divided by 32 equals roughly 8. And then 75 divided by 32 also equals roughly 3. And remember, these numbers are going to be rounded if there are some overlaps. So let's get rid of, we'll change this back to 1. And we'll keep that there. We'll get rid of these 2. And let's see what it looks like to plot an image from our data loader. Or at least have a look at it. Check out the shapes. That's probably the most important point at this time. We've already plotted enough things. So let's iterate through our train data loader. And we'll grab the next one. We'll grab the image and the label. And we're going to print out here. So batch size will now be 1. You can change the batch size if you like. This is just, again, another way of getting familiar with the shapes of our data. So image shape. Let's go image.shape. And we're going to write down here, this shape is going to be batch size. This is what our data loader is going to add to our images. It's going to add a batch dimension. Color channels, height, width, and then print. Let's check out the label shape. Same thing with the labels. It's going to add a batch dimension. Label, and let's see what happens. Oh, we forgot the end of the bracket. Beautiful. So we've got image shape. Our label shape is only 1 because we have a batch size of 1. And so now we've got batch size 1, color channels 3, height, width. And if we change this to 32, what do you think is going to happen? We get a batch size of 32, still 3 color channels, still 64, and now we have 32 labels. So that means within each batch, we have 32 images and we have 32 labels. We could use this with a model. I'm going to change this back to 1. And I think we've covered enough in terms of loading our data sets. How cool is this? We've come a long way. We've downloaded a custom data set. We've loaded it into a data set using image folder, turned it into tensors using our data transform, and now batchified our custom data set in data loaders. We've used these with models before. So if you wanted to, you could go right ahead and build a convolutional neural network to try and find patterns in our image tensors. But in the next video, let's pretend we didn't have this data loader, this image folder class available to us. How could we load our image data set so that it's compatible, like our image data set here? How could we replicate this image folder class so that we could use it with a data loader? Because data loader is part of torchutils.data. You're going to see these everywhere. Let's pretend we didn't have the torchvision.datasets image folder helper function. And we'll see in the next video how we can replicate that functionality. I'll see you there. Welcome back. So over the past few videos, we've been working out how to get our data from our data folder, pizza, steak, and sushi. We've got images of different food data here, and we're trying to get it into tensor format. So we've seen how to do that with an existing data loader helper function, or a dataset function, in image folder. However, what if image folder didn't exist and we needed to write our own custom data loading function? Now, the premise of this is, although it does exist, it's going to be good practice because you might come across a case where you're trying to use a dataset where a pre-built function doesn't exist. So let's replicate the functionality of image folder by creating our own data loading class. So we want a few things. We want to be able to get the class names as a list from our loaded data, and we want to be able to get our class names as a dictionary as well. So the whole goal of this video is to start writing a function or a class that's capable of loading data from here into tensor format, capable of being used with the PyTorch's data loader class like we've done here. So we want to create a data set. Let's start it off. We're going to create another heading here. This is going to be number 5, option 2, loading image data with a custom data set. So we want a few functionality steps here. Number 1 is want to be able to load images from file. 2, want to be able to get class names from the data set. And 3, want to be able to get classes as dictionary from the dataset. And so let's briefly discuss the pros and cons of creating your own custom dataset. We saw option 1 was to use a pre-existing dataset loader helping function from Torch Vision. And it's going to be quite similar if we go Torch Vision datasets. Quite similar if you're using other domain libraries here. They were going to be data loading utilities. But at the base level of PyTorch is torchutils.data.dataset. Now this is the base dataset class. So we want to build on top of this to create our own image folder loading class. So what are the pros and cons of creating your own custom dataset? Well, let's discuss some pros. So one pro would be you can create a dataset out of almost anything, as long as you write the right code to load it in. And another pro is that you're not limited to PyTorch pre-built dataset functions. A couple of cons would be that even though, this is to point number 1, so even though you could create a dataset out of almost anything, it doesn't mean that it will automatically work. It will work. And of course, you can verify this through extensive testing, seeing if your model actually works, if it actually loads data in the way that you want it. And another con is that using a custom dataset requires us to write more code. So often results in us writing more code, which could be prone to errors or performance issues. So typically, if something makes it into the PyTorch standard library or the PyTorch domain libraries, if functionality makes it into here, it's generally been tested many, many times, and it can kind of be verified that it works quite well with, or if you do use it, it works quite well. Whereas if we write our own code, sure, we can test it ourselves, but it hasn't got the robustness to begin with, that is, we could fix it over time, as something that's included in, say, the PyTorch standard library. Nonetheless, it's important to be aware of how we could create such a custom dataset. So let's import a few things that we're going to use. We'll import OS, because we're going to be working with Python's file system over here. We're going to import pathlib, because we're going to be working with file paths. We'll import Torch. We don't need to again, but I'm just doing this for completeness. We're going to import image from PIL, the image class, because we want to be opening images. I'm going to import from torchutils.data. I'm going to import dataset, which is the base dataset. And as I said over here, we can go to datasets, click on torchutils.data.dataset. This is an abstract class representing a dataset. And you'll find that this dataset links to itself. So this is the base dataset class. Many of the datasets in PyTorch, the pre-built functions, subclass this. So this is what we're going to be doing. And there's a few notes here. All subclasses should overwrite getItem, and you should optionally overwrite len. These two methods. We're going to see this in a future video. For now, we're just setting the scene here. So from Torch Vision, we're going to import transforms because we want to not only import our images, but we want to transform them into tensors. And from the Python's typing module, I'm going to import tuple, dict, and list, so we can put type hints when we create our class and loading functions. Wonderful. So this is our instance of Torch Vision.datasets image folder, Torch Vision.datasets.image folder. Let's have a look at the train data. So we want to write a function that can replicate getting the classes from a particular directory and also turning them into an index, or dictionary, that is. So let's build a helper function to replicate this functionality here. In other words, I'd like to write a helper function that if we pass it in a file path, such as pizza steak sushi or this data folder, it's going to go in here and it's going to return the class names as a list, and it's also going to turn them into a dictionary, because it's going to be helpful for later on when we'd like to access the classes and the class to IDX. And if we really want to completely recreate image folder, well, image folder has this functionality, so we'd like that too. So this is just a little high-level overview of what we're going to be doing. I might link in here that we're going to subclass this. So all custom datasets in PyTorch often subclass this. So here's what we're going to be doing. Over the next few videos, we want to be able to load images from a file. Now you could replace images with whatever data that you're working with. The same premise will be here. You want to be able to get the class names from the dataset and want to be able to get classes as a dictionary from the dataset. So we're going to map our samples, our image samples, to their class name by just passing a file path to a function that we're about to write. And some pros and cons of creating a custom dataset. We've been through that. Let's, in the next video, start coding up a helper function to retrieve these two things from our target directory. In the last video, we discussed the exciting concept of creating a custom dataset. And we wrote down a few things that we want to get. We discussed some pros and cons, and we learned that many custom datasets inherit from torch.utils.data.dataset. So that's what we'll be doing later on. In this video, let's focus on writing a helper function to recreate this functionality. So I'm going to title this 5.1, creating a helper function to get class names. I'm going to turn this into Markdown. And if I go into here, so we want a function to, let's write down some steps and then we'll code it out. So we'll get the class names. We're going to use os.scandir. So it's going to scan a directory to traverse a target directory. And ideally, the directory is in standard image classification format. So just like the image folder class, our custom data class is going to require our data already be formatted. in the standard image classification format, such as train and test for training and test images, and then images for a particular class are in a particular directory. So let's keep going. And number 2, what else do we want it to do? We want it to raise an error if the class names aren't found. So if this happens, there might be, we want this to hint at the fact that there might be something wrong with the directory structure. And number 3, we also want to turn the class names into a dict and a list and return them. Beautiful. So let's get started. Let's set up the path directory for the target directory. So our target directory is going to be what? The directory we want to load, directory, if I could spell, we want to load our data from. Let's start with the training dir, just for an example. So target directory, what do we get? So we're just going to use the training folder as an example to begin with. And we'll go print target dir, we'll put in the target directory. Just want to exemplify what we're doing. And then we're going to get the class names from the target directory. So I'll show you the functionality of OS scan dir. Of course, you could look this up in the Python documentation. So class names found, let's set this to be sorted, and then we'll get the entry name, entry.name for entry in list. So we're going to get OS list scan dir of the image path / target directory. Let's see what happens when we do this. Target directory, have we got the right brackets here? Is this going to work? Let's find out. Oh, image path / target directory. What did we get wrong? Oh, we don't need the image path there. Let's just put target directory there. There we go. Beautiful. So we set up our target directory as being the training dir. And so if we just go, let's just do list. What happens if we just run this function here? OS scan dir. Yeah, so there we go. So we have 3 directory entries. So this is where we're getting entry.name for everything in the training directory. So if we look in the training directory, what do we have? Train. And we have 1 entry for pizza, 1 entry for sushi, 1 entry for steak. Wonderful. So now we have a way to get a list of class names. And we could quite easily turn this into a dictionary, couldn't we? Which is exactly what we want to do. We want to recreate this, which we've done. And we want to recreate this, which we've also done. So now let's take this functionality here and let's turn that into a function. All right, what can we do? What do we call this? I'm going to call this def find classes, and I'm going to say that it takes in a directory which is a string, and it's going to return, this is where I imported typing, from Python typing I imported tuple, and I'm going to return a list, which is a list of strings, and a dictionary, which is strings mapped to integers. Beautiful. So let's keep going. We want this function to return, given a target directory, we want it to return these 2 things. We want this function to return, given a target directory, we want it to return these 2 things. So we've seen how we can get a list of the directories in a target directory by using OS scan dir. So let's write finds the classes, the class folder names in a target directory. Beautiful. And we know that it's going to return a list and a dictionary. So let's do step number 1. We want to get the class names by scanning the target directory. We'll go classes. We're going to replicate the functionality we've done above, but for any given directory here. So classes equals sorted entry.name for entry in OS scan dir, and we're going to pass it the target directory if entry.isdir. We're just going to make sure it's a directory as well. And so if we just return classes and see what happens, so find classes, let's pass it in our target directory, which is our training directory. What do we get? Beautiful. So we need to also return class to IDX. So let's keep going. So number 2, is let's go raise an error if class names could not be found. So if not classes, let's say raise file, we're going to raise a file not found error. And then let's just write in here, F couldn't find any classes in directory. So we're just writing some error checking code here. So if we can't find a class list within our target directory, we're going to raise this error and say couldn't find any classes in directory. Please check file structure. And there's another check up here that's going to help us as well to check if the entry is a directory. So finally, let's do number 3. What do we want to do? So we want to create a dictionary of index labels. So computers, why do we do this? Well, computers prefer numbers rather than strings as labels. So we can do this. We've already got a list of classes. So let's just create class to IDX equals class name I for I class name in enumerate classes. Let's see what this looks like, hey? So we'll go class names. And then class to IDX, or we can just return it actually. Do we spell enumerate wrong? Yes, we did. So what this is going to do is going to map a class name to an integer, or to I, for I. Class name in enumerate classes. So it's going to go through this and it's going to go for I. So the first one, 0, is going to be pizza. Ideally, 1 will be
Different thing altogether to be awoken by silence. Your unconscious mind telling you that the sounds you should be hearing are gone. It only takes a groggy minute to piece it together. The refrigerator's silent, no air is flowing through the heating register, the ceiling fan above your head is slowly coming to a stop. The power's out. You check your phone, it's 4 a.m. Nothing you can really do but go back to sleep and hope they get it fixed by daylight. Most of us have experienced a power outage at some point, but they're usually short, lasting on the order of minutes or hours, and they're mostly local, affecting a small area at a time. A wide area interconnection, that's the technical term for a power grid, is designed that way on purpose. It has redundancies, multiple paths that power can take to get to the same destination, and power users and producers are spread out, reducing the chance that they could be impacted all at once. But having everyone interconnected is a vulnerability too, because if things go very wrong, everyone's affected. We're in the midst of a deep dive series on wide-scale outages to the power grid, and a mismatch between supply and demand, like what happened in Texas, is only one of the many reasons that could cause a major blackout. Natural disasters, engineering errors, and deliberate attacks can all completely collapse a grid. And, at least for the first few hours of an outage, you might not even know that what you're experiencing is any more serious than a wayward tree branch tripping the fuse on the transformer outside your house. You wake up 3 hours later, cold, sunlight peeking in through your bedroom window. The power's still off. You grab your cell phone to try and figure out what's going on. It has a full battery from charging overnight, and you have a strong signal too. You try to call a friend, but the call won't go through. You try a few more times, but still nothing more than a friendly voice saying, "All circuits are busy." There is a vast array of pathways that information flows between people across the globe, and they all use grid power to function. Fiber networks use switches and optical terminals distributed throughout the service area. Cable TV and DSL networks have nodes that service around 500 to 1,000 customers each that require power. Cellular networks use base stations mounted on towers or rooftops. Major telecommunications facilities are usually on prioritized grid circuits and may even have redundant power feeds from multiple substations. But even during a blackout, where the entire grid is completely disabled, you might still have service. That's because most telecommunication facilities are equipped with backup batteries that can keep them running during a power outage for 4 to 8 hours. Critical facilities like cellular base stations and data centers often have an on-site backup generator. These generators have enough fuel to extend the resiliency beyond 24 to 48 hours. That said, major emergencies create huge demands on telecommunication services, as everyone's trying to find and share information at once, so you might not be able to get through even if the services are still available. In the US, the federal government works with telecommunication providers to create priority channels so that 911 calls, emergency management communications, and other matters related to public safety can get through, even when the networks are congested. Since you're trying to make a personal call and you aren't enrolled in the Telecommunications Service Priority Program, you're not getting through. Just then, an emergency alert appears on your screen. It says that there's a power grid failure and to prepare for an extended outage. The reality of the situation is just starting to set in. Since most people have a cell phone, wireless emergency alerts have become an important addition to the emergency alert system that connects various levels of government to TV, radio, satellite, and telephone companies to disseminate public warnings and alerts. During a blackout, sharing information isn't just for likes on social media, it's how we keep people safe, connect them with resources, and maintain social order. Two-way communications like cell phones and the internet might not last long during a grid outage, so one-way networks like radio and television broadcasts are essential to keep people informed. These facilities are often equipped with more backup fuel reserves and even emergency provisions for the staff so that they can continue to operate during a blackout for weeks if necessary. Jump ahead a couple of days. Your circumstances start to dictate your experiences heavily. Even an outage of this length can completely upend your life if you, for example, depend on medication that must be refrigerated, or electrically powered medical equipment like a ventilator or dialysis machine. But for many, a blackout on the order of a day or two is still kind of fun, a diversion from the humdrum of everyday life. Maybe you've scrounged together a few meals from what's remaining in your pantry.
Steak, 2 will be sushi. Let's see how this goes. Beautiful, look at that. We've just replicated the functionality of image folder. So now we can use this helper function in our own custom dataset, find classes, to traverse through a target directory such as train. We could do the same for test if we wanted to too. And that way, we've got a list of classes, and we've also got a dictionary mapping those classes to integers. So now, let's in the next video move towards subclassing torchutils.data.dataset, and we're going to fully replicate image folder. So I'll see you there. In the last video, we wrote a great helper function called find classes that takes in a target directory and returns a list of classes and a dictionary mapping those class names to an integer. So let's move forward, and this time we're going to create a custom dataset to replicate image folder. Now, we don't necessarily have to do this, right, because image folder already exists, and if something already exists in the PyTorch library, chances are it's going to be tested well, it's going to work efficiently, and we should use it if we can. But if we needed some custom functionality, we can always build up our own custom dataset by subclassing torch.utils.data.dataset, or if a pre-built dataset function didn't exist, well, we're probably going to want to subclass torchutils.data.dataset anyway. And if we go into the documentation here, there's a few things that we need to keep in mind when we're creating our own custom dataset. All datasets that represent a map from keys to data samples, so that's what we want to do. We want to map keys, in other words, targets or labels, to data samples, which in our case are food images. So we should subclass this class here. Now, to note, all subclasses should overwrite getItem. So getItem is a method in Python, which is going to get an item or get a sample, supporting fetching a data sample for a given key. So for example, if we wanted to get sample number 100, this is what getItem should support. It should return us sample number 100. And subclasses could also optionally override len, which is the length of a dataset. So return the size of the dataset by many sampler implementations and the default options of data loader, because we want to use this custom dataset with data loader later on. So we should keep this in mind when we're building our own custom subclasses of torchutils.data.dataset. Let's see this hands-on. We're going to break it down. It's going to be a fair bit of code, but that's all right. Nothing that we can't handle. So to create our own custom dataset, we want to, number one, first things first is we're going to subclass torch.utils.data.dataset. 2, what do we want to do? We want to init our subclass with a target directory, so the directory we'd like to get data from. as well as a transform if we'd like to transform our data. So just like when we used image folder, we could pass a transform to our data set so that we could transform the data that we were loading. We want to do the same thing. And we want to create several attributes. Let's write them down here. We want paths, which will be the paths of our images. What else do we want? We want transform, which will be the transform we'd like to use. We want classes, which is going to be a list of the target classes. And we want class to IDX, which is going to be a dict of the target classes mapped to integer labels. Now, of course, these attributes will differ depending on your data set, but we're replicating image folder here, so these are just some of the things that we've seen that come with image folder. But regardless of what data set you're working with, there are probably some things that you want across from Universal. You probably want all the paths of where your data is coming from, the transforms you'd like to perform on your data, what classes you're working with, and a map of those classes to an index. So let's keep pushing forward. We want to create a function to load images, because after all, we want to open some images. So this function will open an image. Number 5, we want to overwrite the len method to return the length of our dataset. So just like it said in the documentation, if you subclass using torch.utils.data.dataset, you should overwrite getItem, and you should optionally overwrite len. So we're going to, instead of optionally, we are going to overwrite length. And number 6, we want to overwrite the getItem method to return a given sample when passed an index. Excellent. So we've got a fair few steps here, but if they don't make sense now, it's okay. Let's code it out. Remember our motto, if in doubt, code it out. And if in doubt, run the code. So we're going to write a custom data set. This is so exciting because when you work with pre-built data sets, it's pretty cool in machine learning. But when you can write code to create your own data sets, and that's magic. So number 1 is number 0 is we're going to import Torch Utils dataset. We don't have to rewrite this, we've already imported it, but we're going to do it anyway for completeness. Now, step number 1 is to subclass it. Subclass Torch Utils dataset. So just like when we built a model, we're going to subclass NN module, but in this time we're going to call our class image folder custom, and we're going to inherit from dataset. This means that all the functionality that's contained within Torch Utils dataset, we're going to get for our own custom class. Number 2, let's initialize. So we're going to initialize our custom dataset. And there's a few things that we'd like. Init our subclass with the target directory, the directory we'd like to get data from, as well as a transform if we'd like to transform our data. So let's write a init function, init, and we're going to go self targdir, and targdir is going to be a string, and we're going to set a transform here. We'll set it equal to none. Beautiful. So this way we can pass in a target directory of images that we'd like to load, and we can also pass in a transform, just similar to the transforms that we've created previously. So now we're up to number 3, which is create several attributes. So let's see what this looks like. Create class attributes. So we'll get all of the image paths. So we can do this just like we've done before. Self paths equals list pathlib.path, because what's our target directory going to be? Well, I'll give you a spoiler alert. It's going to be a path like the test directory, or it's going to be the train directory, because we're going to use this once for our test directory and our train directory, just like we used the original image folder. So we're going to go through the target directory and find out all of the paths. So this is getting all of the image paths that support or that follow the file name convention of star/star.jpg. So if we have a look at this, if we passed in the test folder, so test is the folder, star would mean any of these, 1, 2, 3, pizza, steak, sushi, that's the first star. Then slash would go into the pizza directory. The star here would mean any of the file combinations here that end in .jpg. So this is getting us a list of all of the image paths within a target directory. In other words, within the test directory and within the train directory. When we call these two separately. So let's keep going. We've got all of the image paths. What else did we have to do? We want to create transforms. So let's set up transforms. Self.transforms equals transform. Oh, we'll just call that transform actually. Set up transform equals transform. So we're going to get this from here. And I put it as none because transform can be optional. So let's create classes and class to IDX attributes, which is the next one on our list, which is here, classes and class to IDX. Now, lucky us, in the previous video, we created a function to return just those things. So let's go self.classes and self.class to IDX equals find classes. And we're going to pass in the target dir, or the targdir from here. Now, what's next? We've done step number 3. We need, number 4 is create a function to load images. All right, let's see what this looks like. So number 4, create a function to load images. So let's call it load image, and we're going to pass in self, and we'll also pass in an index. So the index of the image we'd like to load, and this is going to return an image.image. So where does that come from? Well, previously we imported from Pill. So we're going to use Python image library or Pillow to import our images. So we're going to, given a file path from here, such as pizza, we're going to import it with the image class. And we can do that using, I believe it's image.open. So let's give that a try. I'll just write a note in here. Opens an image via a path and returns it. So let's write image path equals self. This is why we got all of the image paths above. So self.paths, and we're going to index it on the index. Beautiful. And then let's return image.open image path. So we're going to get a particular image path, and then we're just going to open it. So now we're up to step number 5, override the len method to return the length of our dataset. This is optional, but we're going to do it anyway. So overwrite len. So this just wants to return how many samples we have in our dataset. So let's write that. Def len. So if we call len on our dataset instance, it's going to return just how many numbers there are. So let's write this down. Returns the total number of samples. And this is just going to be simply return length or len of self.paths. So for our target directory, if it was the training directory, we'd return the number of image paths that this code has found out here. And same for the test directory. So next, we're going to go, number 6 is we want to overwrite, we put this up here, the getItem method. So this is required if we want to subclass torch utils dataset. So this is in the documentation here. All subclasses should override getItem. So we want getItem to, if we pass it an index to our dataset, we want it to return that particular item. So let's see what this looks like. Override the getItem method to return a particular sample. And now this method is going to leverage getItem, all of the code that we've created above. So this is going to go take in self, which is the class itself, and it's going to take in an index, which will be of an integer, and it's going to return a tuple of torch.tensor and an integer, which is the same thing that gets returned when we index on our training data. So if we have a look, image label equals train data 0, getItem is going to replicate this. We pass it an index here. Let's check out the image and the label. This is what we have to replicate. So remember, train data was created with image folder from torchvision.datasets. And so we want our getItem to return an image and a label, which is a tuple of a torch tensor, where the image is of a tensor here, and the label is of an integer, which is the label here, the particular index as to which this image relates to. So let's keep pushing forward. I'm going to write down here, returns one sample of data and label, x, and, well, we'll just go xy, so we know that it's a tuple. Beautiful. So let's set up the image. What do we want the image to be? Well, this is where we're going to call on our self.loadImage function, which is what we've created up here. Do you see the customization capabilities of creating your own class? So we've got a fair bit of code here, right? But essentially all we're doing is we're just creating functions that is going to help us load our images into some way, shape, or form. Now, again, I can't stress this enough. Regardless of the data that you're working on, the pattern here will be quite similar. You'll just have to change the different functions you use to load your data. So let's load an image of a particular index. So if we pass in an index here, it's going to load in that image. Then what do? Well, we want to get the class name, which is going to be self.paths, and we'll get the index here, and we can go parent.name. So this expects path in format data folder /class name /image.jpg. That's just something to be aware of. And the class IDX is going to be self.class.idx, and we'll get the class name here. So now we have an image by loading in the image here. We have a class name because our data is going to be, or our data is currently in standard image classification format. You may have to change this depending on the format your data is in. We can get the class name from that, and we can get the class IDX by indexing on our attribute up here, our dictionary of class names to indexes. Now, we have one small little step. This is transform if necessary. So remember our transform parameter up here. If we want to transform our target image, well, let's put in if self.transform. If the transform exists, let's pass the image through that transform. Transform image, and then we're going to also return the class IDX. So do you notice how we've returned a tuple here? This is going to be a torch tensor if our transform exists, and the class IDX is also going to be returned, which is what we want here, x and y, which is what gets returned here. Image as a tensor, label as an integer. So return data, label, x, y, and then if the transform doesn't exist, let's just return image class IDX. Return untransformed image and label. Beautiful. So that is a fair bit of code there. So you can see the pro of label. Beautiful. So that is a fair bit of code there. So you can see the pro of subclassing torch utils data.dataset is that we can customize this in almost any way we wanted to load whatever data that we're working with, or almost any data. However, because we've written so much code, this may be prone to errors, which we're going to find out in the next video to see if it actually works. But essentially all we've done is we've followed the documentation here, torch.utils data.dataset, to replicate the functionality of an existing data loader function, namely image folder. So if we scroll back up, ideally, if we've done it right, we should be able to write code like this, passing in a root directory, such as a training directory, a particular data transform, and we should get very similar instances as image folder, but using our own custom dataset class. So let's try that out in the next video. So now we've got a custom image folder class that replicates the functionality of the original image folder data loader class, or dataset class that is. Let's test it out. Let's see if it works on our own custom data. So we're going to create a transform here so that we can transform our images, raw JPEG images, into tensors, because that's the whole goal of importing data into PyTorch. So let's set up a train transforms compose. We're going to set it to equal to transforms.compose, and I'm going to pass in a list here that's going to be transforms. We're going to resize it to 6464, whatever the image size. We'll reduce it down to 6464. Then we're going to go transforms.random horizontal flip. We don't need to necessarily flip them, but we're going to do it anyway just to see if it works. And then let's put in here transforms.toTensor, because our images are getting opened as a PIL image using image.open, but now we're using the toTransform transform from PyTorch or torchvisions.transforms. So I'll just put this here from torchvision.transforms. That way you know we're importing transforms there. And let's create one for the test dataset as well, test transforms. We'll set this up. Oh, excuse me. I need to just go import transforms. And let's go transforms.compose, and we'll pass in another list. We're going to do the exact same as above. We'll set up resize, and we'll set the size equal to 6464. And then transforms, we're going to go .toTensor. We're going to skip the data augmentation for the test data, because typically you don't manipulate your test data in terms of data augmentation. You just convert it into a tensor rather than manipulate its orientation, shape, size, etc., etc. So let's run this. And now let's see how image folder custom class works. Test out image folder custom. Let's go, we'll set up the train data custom is equal to image folder custom, and then we'll set up the tag_dir, which is equal to the training directory, and then we'll pass in the transform, which is equal to the train transforms, which we just created above, train transforms. And then we're going to, I think that's all we need actually. We only had two parameters there. We're not going to use a target transform because our labels, we've got a helper function to transform our labels. So test data custom is going to be image folder custom, and I'm going to set up the tag_dir to be equal to the test directory, and the transform is going to be the test transforms from the cell above there. And what's Colab telling me there? Oh, I'm going to set that up. Did we spell something? Oh, we spelled it wrong. Train transforms. There we go. Beautiful. Now let's have a look at our train data and test. Data custom, see if it worked. What do we have? Oh, we have an image folder custom. Well, it doesn't give us as much rich information as just checking it out as it does for the train data, but that's okay. We can still inspect these. So this is our original one made with image folder, and we've got now train data custom and test data custom. Let's see if we can get some information from these. So let's check the original length of the train data and see if we can use the len method on our train data custom. Did that work? Wonderful. Now how about we do it for the original test data made with image folder and our custom version made with test data or image folder custom. Beautiful, that's exactly what we want. And now let's have a look at the train data custom. Let's see if the classes attribute comes up. .classes, and we'll just leave that there. We'll do the class.idx. Yes, it is. So this attribute here is, I wonder if we get information from Google Colab. Loading. What do we get? Oh, classes to IDX, classes, load image, paths, transform. So if we go back up here, all these attributes are from here. Paths, transform, classes, class to IDX, as well as load image. So this is all coming from the code that we wrote, our custom dataset class. So let's keep pushing forward. Let's have a look at the class to IDX. Do we get the same as what we wanted before? Yes, we do. Beautiful. A dictionary containing our string names and their integer associations. So let's now check for equality. We can do this by going check for equality between original image folder dataset and image folder custom dataset. Now, we've kind of already done that here, but let's just try it out. Let's go print. Let's go train data custom.classes. Is that equal to train, oh, I don't want 3 equals, train data, the original one, .classes, and also print, let's do test data custom.classes. Is this equal to test data, the original one, classes? True and true. Now, you can try this out. In fact, it's a little exercise to try it out to compare the others, but congratulations to us. We have replicated the main functionality of the image folder dataset class. And so the takeaways from this is that whatever data you have, PyTorch gives you a base dataset class to inherit from, and then you can write a function or a class that somehow interacts with whatever data you're working with. So in our case, we load in an image, and then as long as you override the len method and the get item method and return some sort of values, well, you can create your own dataset loading function. How beautiful is that? So that's going to help you work with your own custom datasets in PyTorch. So let's keep pushing forward. We've seen analytically that our custom dataset is quite similar to the original PyTorch torchvision.datasets image folder dataset. But you know what I like to do? I like to visualize things. So let's in the next video create a function to display some random images from our train data custom class. It's time to follow the Data Explorer's motto of visualize, visualize, visualize. So let's create another section. I'm going to write here a title called create a function to display random images. And sure, we've had a look at the different attributes of our custom dataset. We see that it gives back a list of different class names. We see that the lengths are similar to the original, but there's nothing quite like visualizing some data. So let's go in here. We're going to write a function, a helper function. So step number 1, we need to take in a dataset. So one of the datasets that we just created, whether it be train data custom or train data, and a number of other parameters, such as class names and how many images to visualize. And then step number 2 is to prevent the display getting out of hand, let's cap the number of images to see at 10, because look, if our dataset is going to be thousands of images and we want to put in a number of images to look at, let's just make sure the maximum is 10. That should be enough. So we'll set the random seed for reproducibility. Number 4 is let's get a list of random samples. So we want random sample indexes. I'll just get rid of this S. From, what do we want it from? From the target dataset. So we want to take in a data set, and we want to count the number of images we're seeing. We want to set a random seed. And do you see how much I use randomness here to really get an understanding of our data? I really, really, really love harnessing the power of randomness. So we want to get a random sample of indexes from all of our data set. And then we're going to set up a matplotlib plot. Then we want to loop through the random sample images and plot them with matplotlib. And then as a side to this one, step 7 is we need to make sure the dimensions of our images line up with matplotlib. So matplotlib needs height, width, color channels. All right, let's take it on, hey? So number 1 is create a function to take in a dataset. So we're going to call this def, let's call it def display random images. It's going to be one of our helper functions. We've created a few type of functions like this, but let's take in a dataset which is torch utils of type, that is, of type dataset. Then we're going to take in classes, which is going to be a list of different strings. So this is going to be our class names for whichever dataset we're using. I'm going to set this equal to none. And then we're going to take in n, which is the number of images we'd like to plot. And I'm going to set this to 10 by default, so we can see 10 images at a time, 10 random images, that is. Do we want to display the shape? Let's set that equal to true, so that we can display what the shape of the image is, because we're passing it through our transform as it goes into a data set. So we want it going to be an integer. And we'll set that to none to begin with as well. Okay, so step number 2, what do we have above? We have to prevent the display getting out of hand, let's cap the number of images to see at 10. So we've got n, this by default it's going to be 10, but let's just make sure that it stays there. Adjust display if n is too high. So if n is greater than 10, let's just readjust this. Let's set n equal to 10 and display shape. We'll turn off the display shape because if we have 10 images, our display may get out of hand. So just print out here. For display purposes, n shouldn't be larger than 10, setting to 10 and removing shape display. Now I only know this because I've had experience cooking this dish before. In other words, I've written this type of code before. So you can customize. The beautiful thing about Python and PyTorch is you can customize these display functions in any way you see fit. So step number 3, what are we doing? Set the random seed for reproducibility. Okay, set the seed. So if seed, let's set random.seed equal to that seed value, and then we can keep going. So number 4 is let's get some random sample indexes. So we can do that by going get random sample indexes. Which is step number 4 here. So we've got a target data set that we want to inspect, and we want to get some random samples from that. So let's create a random samples IDX list, and I'm going to randomly sample from a length of our data set, or sorry, a range of the length of our data set. And I'll show you what this means in a second. And the K, oh, excuse me, have we got enough brackets there? I always get confused with the brackets. The K is going to be N. So in this case, I want to randomly sample 10 images from the length of our data set, or 10 indexes. So let's just have a look at what this looks like. We'll put in here our train data custom here. So this is going to take a range of the length of our train data custom, which is what? 225. We looked at that before, just up here. Length of this. So between 0 and 255, we're going to get 10 indexes if we've done this correctly. Beautiful. So there's 10 random samples. So between 0 and 255, we're going to get 10 indexes if we've done this correctly. Beautiful. So there's 10 random samples from our train data custom, or 10 random indexes, that is. So we're up to step number 5, which was loop through the random sample images, or indexes. Let's create this to indexes, and plot them with matplotlib. So this is going to give us a list here. So let's go loop through random indexes and plot them with matplotlib. Beautiful. So for I target sample in enumerate, let's enumerate through the random samples IDX list, and then we're going to go targ image and targ label, because all of the samples in our target dataset are in the form of tuples. So we're going to get the target image and the target label, which is going to be dataset targ sample. We'll take the index, so it might be one of these values here. We'll index on that, and the 0th index will be the image, and then we'll go on the dataset as well. We'll take the targ sample index, and then the index number 1 will be the label of our target sample. And then number 7, oh, excuse me, we've missed a step. That should be number 6. Did you catch that? Number 5 is set up plot. So we can do this quite easily by going plot figure. This is so that each time we iterate through another sample, we're going to have quite a big figure here. So we set up the plot outside the loop so that we can add a plot to this original plot here. And now this is number 7, where we make sure the dimensions of our images line up with matplotlib. So if we recall, by default, PyTorch is going to turn our image dimensions into what?
Enjoyed some candlelit conversations with neighbors, seen more stars in the night sky than you ever have in your life. But after those first 48 hours, things are starting to get more serious. You ponder how long you can stay in your home before needing to go out for supplies as you head into the kitchen to get a glass of water. You open the tap and nothing comes out. A public water supply is another utility highly dependent on a functioning electrical grid. Pumping, cleaning, and disinfecting water to provide a safe source to everyone within a city is a power-intensive ordeal. Water's heavy, after all, and just moving it from one place to another takes a tremendous amount of energy. Most cities use a combination of backup generators and elevated storage to account for potential emergencies. Those elevated tanks, whether they're water towers or just ground-level basins built on hillsides, act kind of like batteries to make sure the water distribution system stays pressurized even if pumps lose power. But those elevated supplies don't last forever. Every state has its own rules about how much is required. In Texas, large cities must have at least 200 gallons or 750 liters of water stored for every connection to the system, and half of that needs to be in elevated or pressurized tanks so that it will still flow into the pipes if the pumps aren't working. Average water use varies quite a bit by location and season, but that amount of storage is roughly enough to last a city 2 days under normal conditions. Combine the backup storage with the backup generation system at a typical water utility, and maybe they can stretch to 3 or 4. Without a huge mobilization of emergency resources, water can quickly become the most critical resource in an urban area during a blackout. But don't forget the related utility we depend on as well: sewage collection. Lift stations that pump raw sewage and treatment plants that clean it to a level where it's safe to release back into the environment are energy-intensive processes as well. Most states require that lift stations and treatment plants have backup power supplies or enough storage to avoid overflows during an outage, but usually those requirements are for short-term disruptions. When power is lost for more than a day or two, these facilities won't be able to continue functioning without additional fuel and maintenance. Even in the best case scenario, that means raw wastewater in the sewers will have to bypass treatment plants and be discharged directly into waterways like rivers and oceans. In the worst case, sewers and lift stations will overflow, exposing the people within cities to raw sewage and creating a public health emergency. Flash forward to a week after the start of the blackout, and any fun from the change of pace is long gone. You still keep your cell phone battery charged from your car, but you rarely get a signal, and phone calls almost never connect. Plus, your car is almost out of gasoline, and the fuel at filling stations has long been sent to backup generators at critical facilities. You are almost certainly running low on food and water after a week, even if you've been able to share or barter with neighbors or visit one of the rare stores that was willing to open their doors and accept cash. By now, only the most prioritized facilities like hospitals and radio stations, plus those with solar or wind charging systems, still have a functioning backup power supply. Everything else is just dead. And now you truly get a sense of how complex and interconnected our systems of infrastructure are, because there's almost nothing that can frustrate the process of restoring power than a lack of power itself. Here's what I mean.
color channels first. However, Matplotlib prefers color channels last. So let's go adjust tensor dimensions for plotting. So let's go targ image. Let's call this target. Image adjust equals targ image dot commute, and we're going to alter the order of the indexes. So this is going to go from color channels, or the dimensions that is, height, width, and we're going to change this width, if I could spell, to height, width, color channels. Beautiful. That one will probably catch you off guard a fair few times, but we've seen it a couple of times now, so I'm going to keep going with this. Plot adjusted samples. So now we can add a subplot to our Matplotlib plot, and we want to create, we want one row of n images. This will make a lot more sense once we visualize it. And then for the index, we're going to keep track of I plus 1. So let's keep going. So then we're going to go plot im show, and I'm going to go targ image adjust. So I'm going to plot this image here. And then let's turn off the axis. And we can go, if the classes variable exists, which is up here, a list of classes, let's adjust the title of the plot to be the particular index in the class list. So title equals f class, and then we're going to put in here classes, and we're going to index on that with the targ label index, which is going to come from here, because that's going to be a numerical format. And then if display shape, let's set the title equal to title plus f. I'm going to go new line shape. This is going to be the shape of the image. Targ image adjust dot shape. And then we'll set the title to plt dot title. So you see how if we have display shape, we're just adjusting the title variable that we created here, and then we're putting the title onto the plot. So let's see how this goes. That is quite a we created here, and then we're putting the title onto the plot. So let's see how this goes. That is quite a beautiful function. Let's pass in one of our data sets and see what it looks like. Let's plot some random images. So which one should we start with first? So let's display random images from the image folder created dataset. So this is the inbuilt PyTorch image folder. Let's go display random images, the function we just created above. We're going to pass in the train data, and then we can pass in the number of images. Let's have a look at 5. And the classes is going to be the class names, which is just a list of our different class names. And then we can set the seed. We want it to be random, so we just set the seed to equal none. Ooh, doesn't that look... Good. So this is from our original train data made with image folder. So option number 1 up here. Option 1. There we go. And we pass in the class name. So this is sushi, resized to 64, 64, 3. Same with all of the others, but from different classes. Let's set the seed to 42, see what happens. I get these images. We got a sushi, we got a pizza, we got pizza, sushi, pizza. And then if we try a different one, we just go none. We get random images again. Wonderful. Now let's write the same code, but this time using our train data custom dataset. So display random images from the image folder custom dataset. So this is the one that we created. Display random images. I'm going to pass in train data custom, our own dataset. Oh, this is exciting. Let's set n equal to 10 and just see how far we can go with our plot. Or maybe we set it to 20 and just see if our code for adjusting the plot makes sense. class names, and seed equals, I'm going to put in 42 this time. There we go. For display purposes, n shouldn't be larger than 10, setting to 10 and removing shape display. So we have a steak image, a pizza image, pizza, steak, pizza, 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 steak, pizza. If we turn off the random seed, we should get another 10 random images here. Beautiful. Look at that. Steak, steak, sushi, pizza, steak, sushi class. I'm reading out the different things. You see a pizza. Pizza, pizza, pizza. Okay, so it looks like our custom dataset is working from both a qualitative standpoint, looking at the different images, and a quantitative. How about we change it to 5 and see what it looks like? Do we have a different shape? Yes, we do. The same shape as above. Wonderful. Okay, so we've got train data custom, and we've got train data which is made from image folder, but the premises remain. We've built up a lot of different ideas, and we're looking at things from different points of view. We are getting our data from the folder structure here into tensor format. So there's still one more step that we have to do, and that's go from dataset to data loader. So in the next video, let's see how we can turn our custom loaded images, train data custom and test data custom, into data loaders. So you might want to go ahead and give that a try yourself. We've done it before up here. Turn loaded images into data loaders. We're going to replicate the same thing as we did in here for our option number 2, except this time we'll be using our custom dataset. I'll see you in the next video. Aren't they some good looking images? And even better that they're from our own custom dataset. Now we've got one more step. We're going to turn our dataset into a data loader. In other words, we're going to batchify all of our images so they can be used with a model. And I gave you the challenge of trying this out yourself in the last video, so I hope you gave that a go, but let's see what that might look like in here. So I'm going to go 5.4. Let's go, what should we call this? So turn custom loaded images into data loaders. So this is just goes to show that we can write our own custom dataset class, and we can still use it with PyTorch's data loader. So let's go from utils torch.utils, that is, utils.data, import data loader. We'll get that in here. We don't need to do that again, but I'm just doing it for completeness. So we're going to set this to train data loader custom, and I'm going to create an instance of data loader here. And then inside, I'm going to pass the data set, which is going to be train data custom. I'm just going to set a universal parameter here in capitals for batch size equals 32, because we can come down here, we can set the batch size, we're going to set this equal to 32, or in other words, the batch size parameter we set up there. We can set the number of workers here as well. If you set to 0, let's go see what the default is actually. Torch, utils, data, loader. What's the default for number of workers? 0. Okay, beautiful. And recall that number of workers is going to set how many cores load your data with a data loader, and generally higher is better. But you can also experiment with this value and see what value suits your model and your hardware the best. So just keep in mind that number of workers is going to alter how much compute your hardware that you're running your code on uses to load your data. So by default, it's set to 0, and then we're going to shuffle the training data. Wonderful. And let's do the same for the test data loader. We'll create test data loader custom, and I'm going to create a new instance. So let me make a few code cells here of data loader. I'm going to create a data set, or pass in a data set parameter as the test data custom. So again, these data sets are what we've created using our own custom data set class. We're going to set the batch size equal to batch size, and set the num workers equal to 0. In a previous video, we've also set it to CPU count. You can also set it to 1. You can hard code it to 4. All depends on what hardware you're using. I like to use os.cpu count. And then we're not going to shuffle the test data. False. Beautiful. And let's have a look at what we get here. Train data loader custom and test data loader custom. And actually, I'm just going to reset this. Instead of being OS CPU count, I'm going to put it back to 0, just so we've got it in line with the one above. And of course, num workers, we could also set this num workers equals 0 or os.cpu count. And then we could come down here and set this as num workers and num workers. And let's have a look to see if it works. Oh, beautiful. So we've got two instances of utils.data.data loader. Now let's just get a single sample from the train data loader here, just to make sure the image shape and batch size is correct. Get image and label from custom data loader. We want image custom, and I'm going to go label custom equals next, and I'm going to iter over the train data loader custom. And then let's go print out the shapes. We want image custom dot shape and label custom. Do we get a shape here? Beautiful, there we go. So we have shape here of 32 because that is our batch size. Then we have 3 color channels, 64, 64, which is in line with what? Which is in line with our transform that we set all the way up here. Transform, we transform our image. You may want to change that to something different depending on the model you're using, depending on how much data you want to be comprised within your image. Recall, generally a larger image size encodes more information. And this is all coming from our original ImageFold custom dataset class. So look at us go. And I mean, this is a lot of code here, or a fair bit of code, right? But you could think of this as like you write it once, and then if your dataset continues to be in this format, well, you can use this over and over again. So you might put this image folder custom into a helper function file over here, such as dataset.py or something like that, and then you could call it in future code instead of rewriting it all the time. And so that's just exactly what PyTorch has done with torchvision.datasets.image folder. So we've got some shapes here, and if we wanted to change the batch size, what do? We just change it like that. 64. Remember, a good batch size is also a multiple of 8 because that's going to help out computing, and batch size equals 1. We get a batch size equal of 1. Whew. We've been through a fair bit, but we've covered a very important thing, and that is loading your own data with a custom data set. So generally, you will be able to load your own data with an existing data loading function or dataset function from one of the Torch domain libraries, such as Torch Audio, Torch Text, Torch Vision, Torch Rec, and later on when it's out of beta, Torch Data. But if you need to create your own custom one, well, you can subclass torch.utils.data.dataset and then add your own functionality to it. So let's keep pushing forward. Previously, we touched a little bit on transforming data, and you may have heard me say that Torch Vision transforms can be used for data augmentation. And if you haven't, that is what the documentation says here. But data augmentation is manipulating our images in some way, shape, or form so that we can artificially increase the diversity of our training data set. So let's have a look at that more in the next video. I'll see you there. Over the last few videos, we've created functions and classes to load in our own custom dataset. And we learned that one of the biggest steps in loading a custom dataset is transforming your data, particularly turning your target data into tensors. And we also had a brief look at the Torch Vision transforms module, and we saw that there's a fair few different ways that we can transform our data. And that one of the ways that we can transform our image data is through augmentation. And so if we went into the illustration of transforms, let's have a look at all the different ways we can do it. We've got resize, it's going to change the size of the original image. We've got center crop, which will crop. We've got 5 crop. We've got grayscale. We've got random transforms. We've got Gaussian blur. We've got random rotation, random affine, random crop. We could keep going. And in fact, I'd encourage you to check out all of the different options here. But, oh, there's auto augment. Wonderful. There's random augment. This is what I was hinting at. data augmentation. Do you notice how the original image gets augmented in different ways here? So it gets artificially changed. So it gets rotated a little here, it gets darkened a little here, or maybe brightened, depending how you look at it. It gets shifted up here, and then the colors kind of change here. And so this process is known as data augmentation, as we've hinted at. And we're going to create another section here, which is number 6, other forms of transforms. And this is data augmentation. So how could you find out about what data augmentation is? Well, you could go here, what is data augmentation? And I'm sure there's going to be plenty of resources here. Wikipedia, there we go. Data augmentation. In data analysis, are techniques used to increase the amount of data by adding slightly modified copies of already existing data or newly created synthetic data from existing data. So I'm going to write down here, data augmentation is the process of artificially adding diversity to your training data. Now, in the case of image data, this may mean applying various image transformations to the training images. And we saw a whole bunch of those in the Torch Vision Transforms package. But now, let's have a look at one type of data augmentation in particular, and that is trivial augment. But just to illustrate this, I've got a slide here ready to go. We've got what is data augmentation, and it's looking at the same image, but from different perspectives. And we do this, as I said, to artificially increase the diversity of a data set. So if we imagine our original image is over here on the left, and then if we wanted to rotate it, we could apply a rotation transform. And then if we wanted to shift it on the vertical and the horizontal axis, we could apply a shift transform. And if we wanted to zoom in on the image, we could apply a zoom transform. And there are many different types of transforms, as I've got a note here. There are many different kinds of data augmentation, such as cropping, replacing, shearing, and this slide only demonstrates a few. But I'd like to highlight another type of data augmentation, and that is one used to recently train PyTorch Torch Vision image models to state-of-the-art levels. So let's take a look at one particular type of data augmentation used to train PyTorch vision models to state-of-the-art levels. Now, just in case you're not sure why we might do this, we would like to increase the diversity of our training data so that our images become harder for our model to learn, or it gets a chance to view the same image from different perspectives so that when you use your image classification model in practice, it's seeing the same sort of images but from many different angles. So hopefully it learns patterns that are generalizable to those different angles. So this practice hopefully results in a model that's more generalizable to unseen data. And so if we go to Torch Vision, state-of-the-art, here we go. So this is a recent blog post by the PyTorch team, how to train state-of-the-art models, which is what we want to do. State-of-the-art means best in the business, otherwise known as SOTA. You might see this acronym quite often, using Torch Vision's latest primitives. So Torch Vision is the package that we've been using to work with vision data, and Torch Vision has a bunch of primitives, which are, in other words, functions, that help us train really good performing models. So blog post here. And if we jump into this blog post, and if we scroll down, we've got some improvements here. So there's an original ResNet 50 model. ResNet 50 is a common computer vision architecture. So accuracy at 1. So what do we have? Well, let's just say they get a boost in what the previous results were. So if we scroll down, there is a type of data augmentation here. So if we add up all of the improvements that they used, so there's a whole bunch here. Now, as your extra curriculum, I'd encourage you to look at what the improvements are. You're not going to get them all the first go, but that's all right. Blog posts like this come out all the time, and the recipes are continually changing. So even though I'm showing you this now, this may change in the future. So I just scrolled down to see if this table showed us what the previous results were. Doesn't look like it does. Oh no, there's the baseline. So 76, and with all these little additions, it got right up to nearly 81. So nearly a boost of 5% accuracy. And that's pretty good. So what we're going to have a look at is trivial augment. So there's a bunch of different things such as learning rate optimization, training for longer. So these are ways you can improve your model. Random erasing of image data, label smoothing, you can add that as a parameter to your loss functions, such as cross entropy loss, mix up and cut mix, weight decay tuning, fixed res mitigations, exponential moving average, which is EMA, inference resize tuning. So there's a whole bunch of different recipe items here, but we're going to focus on one. We're going to break it down. Let's have a look at trivial augment. So we'll come in here. Let's look at trivial augment. So if we wanted to look at trivial augment, can we find it in here? Oh yes, we can. It's right here. Trivial augment. So as you'll see, if you pass an image into trivial augment, it's going to change it in a few different ways. So if we go into here, let's write that down. So let's see this in action on some of our own data. So we'll import from Torch Vision, import transforms, and we're going to create a train transform, which is equal to transforms.compose. We'll pass it in there. And this is going to be very similar to what we've done before in terms of composing a transform. What do we want to do? Well, let's say we wanted to resize one of our images, or an image going through this transform. Let's change its size to 224, which is a common size in image classification. And then it's going to go through transforms. We're going to pass in trivial augment wide. And there's a parameter here, which is number of magnitude bins, which is basically a number from 0 to 31, 31 being the max, of how intense you want the augmentation to happen. So say we only put this as 5. our augmentation would be of intensity from 0 to 5. And so in that case, the maximum wouldn't be too intense. So if we put it to 31, it's going to be the max intensity. And what I mean by intensity is, say, this rotation, if we go on a scale of 0 to 31, this may be a 10, whereas 31 would be completely rotating. And same with all these others, right? So then if we go transforms dot to tensor. Wonderful. So there we've just implemented trivial augment. How beautiful is that? That is from the PyTorch Torch Vision transforms library. We've got trivial augment wide, and it was used, trivial augment, to train the latest state-of-the-art vision models in the PyTorch Torch Vision models library or models repository. And if you wanted to look up trivial augment, how could you find that? You could search it. Here's the paper if you'd like to read it, how it's implemented. It's actually a very, very, I would say, let's just say trivial augment. I didn't want to say simple because I don't want to downplay it. Trivial augment leverages the power of randomness quite beautifully. So I'll let you read more on there. I would rather try it out on our data and visualize it first. Test transform. Let's go transforms, compose. And you might have the question of, which transforms should I use with my data? Well, that's the million-dollar question, right? That's the same thing as asking, which model should I use for my data? There's a fair few different answers there, and my best answer will be try out a few, see what worked for other people, like we've done here, by finding that trivial augment worked well for the PyTorch team, and try that on your own problems. If it works well, excellent. If it doesn't work well, you can always, excuse me, we've got a spelling mistake. If it doesn't work well, you can always set up an experiment to try something else. So let's test out our augmentation pipeline. So we'll get all the image paths. We've already done this, but we're going to do it anyway again, just to reiterate. We've covered a fair bit here, so I might just rehash on a few things. We're going to get list, image path, which is our, let me just show you, our image path. We just want to get all of the images within this file. So we'll go image path.glob, glob together all the files and folders that match this pattern. And then if we check, what do we get? We'll check the first 10. Beautiful. And then we can leverage our function from before to plot some random images. Plot random images. We'll pass in, or plot transformed, random transformed images. That's what we want. Let's see what it looks like when it goes through our trivial augment. So image paths equals image path list. This is a function that we've created before, by the way. Transform equals train transform, which is the transform we just created above. That contains trivial augment. And then we're going to put n equals 3 for 5 images, and we'll do seed equals none to plot, n equals 3 for 3 images, not 5. Beautiful. And we'll set the seed equals none, by the way. So look at this. We've got class pizza. Now, trivial beautiful. And we'll set the seed equals none, by the way. So look at this. We've got class pizza. Now, trivial augment, it resized this. Now, I'm not quite sure what it did to transform it per se. Maybe it got a little bit darker. This one looks like the colors have been manipulated in some way, shape, or form. And this one looks like it's been resized, and not too much has happened to that one from my perspective. So if we go again, let's have a look at another 3 images. So trivial augment works. And what I said before, it harnesses the power of randomness. It kind of selects randomly from all of these other augmentation types and applies them at some level of intensity. So all of these ones here, trivial augment, is just going to select some at random and then apply them at some random intensity from 0 to 31, because that's what we've set on our data. And of course, you can read a little bit more in the documentation, or sorry, in the paper here. But I like to see it happening. So this one looks like it's been cut off over here a little bit. This one, again, the colors have been changed in some way, shape, or form. This one's been darkened. And so, do you see how we're artificially adding diversity to our training data set? So instead of all of our images being this one perspective like this, we're adding a bunch of different angles and telling our model, hey,
is running at 60 FPS on next-gen consoles and capable PCs. That apply equally to the broadcast and live events space. Stage operators get a new dedicated in-camera VFX editor, tailored to their specific tasks such as light card placement and editing on in-display walls. It also provides access to new color correction tools. The virtual camera system is now more responsive and reliable and features an updated UI with a modern, camera-focused design. And adding an EXR or movie file to a level or sequencer is now just a matter of drag and drop from the content browser. Character animators have plenty to look forward to in this release. The machine learning deformer lets you generate high-fidelity approximations of deformation rigs from Maya that execute in real time in UE. On another front, Control Rig continues to expand toward fully procedural rigging. Now you can create a single Control Rig asset and use it for characters with different skeletal proportions and properties. Improvements to Sequencer include support for constraints, letting you quickly and easily create and animate relationships between any Control Rig or actor. For example, making a camera always follow a character, or keeping a character's hands on a steering wheel. Enhancements to the modeling toolset include new functions for geometry scripting, UV editor improvements to handle more complex assets, and a new pattern tool that lets you tile one or more selected meshes along a line, grid, or circle oriented on a movable 3D plane. Last but not least, MetaSounds now offers additional node types, support for various multi-channel output formats, and enhanced usability. We've also introduced Soundscape, a plugin for procedural ambient sound generation. These are just some of the highlights of what's new in Unreal Engine 5.1. You can find out more on our What's New page, where you'll also find a link to download the release if you're a new user. Otherwise, it's available right from your Epic Games launcher. Enjoy! Enjoy!
Warm-up session.
Hi, I'm Rick Steves, and it's Christmas time in Europe. From manger scenes to mistletoe, from Norway to Rome, we're celebrating all over the continent. Bon Natale, Fröhliche Weihnachten, Joyeux Noël, Merry Christmas, and thanks for joining us. In Melting Pot America, Christmas is celebrated year after year with traditions that came over on the boat with our ancestors. In this holiday special, we're traveling back to the old country, to places of rich variety and deep roots. We'll explore the history behind our much-loved traditions. Joining friends and families across Europe, we'll discover a Christmas that's both familiar and different.
England is filled with voices singing in the season. The short days around the solstice bring Norwegians out to celebrate the light of Christmas. Families, friends, and food are the centerpiece of the French Noel. An angelic Christmas presence fills Germany and Austria with magical wonder. Italy reveals the sacred nature of the season, from its countryside to its holiest shrines. Nature, in all its wintry glory, seems to shout out the joy of the season in Switzerland. And everywhere, Christmas is celebrated with family, including my own, as together, Europe remembers the quiet night that holiest family came to be.
While each European culture gives Christmas its own special twist, they all follow the same story of how the Son of God was born on earth, as told in the Bible and illustrated over the centuries by great artists.
The Christmas story begins with the Annunciation. An angel sent from God with a message for a young woman whose name was Mary. And the angel said, "Fear not, for thou shalt bring forth a son, and you will name him Jesus. And he shall be called the Son of the Most High, and his kingdom will have no end." And it came to pass that there went out a decree from Caesar Augustus that all the world should be taxed. And Joseph, a carpenter from Nazareth, went to Bethlehem to be taxed with Mary, who was expecting a child. And while they were there, she brought forth her firstborn son and laid him in a manger, because there was no room in the inn. In that region there were shepherds keeping watch over their flocks by night. An angel of the Lord came to them and said, "Fear not, for behold, I bring you good tidings of great joy. For unto you is born on this day in the city of David a Savior, who is Christ the Lord." And suddenly there was a multitude of angels proclaiming, "Glory to God in the highest, and on earth peace and goodwill to all." And the shepherds said, "Let us go to Bethlehem," where they found Mary and Joseph and the babe lying in a manger.
But in the 4th century, a pope declared December 25th to be the official birthday of Jesus. Why that day? Well, Christianity was newly legal in the Roman Empire, and the clever pope figured it would be smart if the biggest Christian festival coincided with the biggest pagan one, winter solstice. And throughout the land, people, Christians celebrating the birth of the sun, and pagans celebrating the return of the sun, have been rejoicing ever since.
For scenes straight out of a box of old-fashioned Christmas cards, we head to England, to the city of Bath. Here in the heart of the old town, near the magnificent medieval abbey, Bath hosts an annual Christmas market.
Mulled wine, please.
Carols are a deeply ingrained part of the English Christmas tradition. The custom goes back to Shakespeare's day. Today, young and old sing their way through the season. Here, the Bath Abbey Choir of Boys and Men are performing a carol concert by candlelight. As is the case just about anywhere, it's in the countryside that families celebrate Christmas in the most down-to-earth style. My friends Maddie and Paul and their kids, Theo and Layla, are looking for a living tree, which they'll decorate and then plant at home.
About the right size? Yeah, okay. Brilliant, I like it.
It's a new twist on an old tradition, with a wink to the nature-worshipping pagans who once haunted these parts. Decorating with greens goes back to the Druids who adorned their temples with swags of evergreen. For pagans, living greens in the dead of winter represented the persistence of life. And for Christians, evergreens are a reminder of the gift of everlasting life. During this hectic season, getting together to bake Christmas goodies while the little ones decorate edible ornaments is a fine way for busy mums to enjoy some time together. Maddie's recipe for mince pies harkens back to the days of Henry VIII. Back then, the dried fruits, spices, and shredded meat for the filling were so expensive that only the wealthy could afford to make a mince pie. According to tradition, 12 pies should be eaten during the 12 days of Christmas to ensure good luck each month of the coming year.
Forget those mince pies, Maddie.
But it's the Christmas pudding that's the real centerpiece of a traditional English holiday meal.
Now bring us a figgy pudding. Now bring us a figgy pudding. Now bring us a...
Simpler, less commercial style of Christmas, and that's reflected in their family traditions. Little Theo's and Layla's wouldn't always have been so involved in the family activities. Childhood, as we know it, really began in 19th century England with the new middle class. And at Christmas, those stern Victorians gave themselves permission to indulge their children. The English tradition of caroling starts very young. We're visiting Theo's school as the students take center stage at the 14th century village church for a very special Christmas concert. Christmas is drawing near, and tonight, these lucky kids are taking a train through the woods to meet Santa, or, as the English know him, Father Christmas.
Come on in now. Now come on in and stand just there. You stand just there. You come across there, that's right. And tell me your names. Now, what's your name?
Dylan.
Hello, and what's your name?
Kate.
And what's your name?
Jack.
Oh, well done. Now then, most important, what do you want for Christmas?
I don't know.
Just some surprises. I'm very good at surprises. And what do you want?
Well, I haven't written my list down yet.
Haven't you? So we're going to wait for your list, and when it comes, I'll be ready for it. Now, are you going to do something for me? Are you going to leave me something out on Christmas Eve?
Yes.
What are you going to leave me?
Mince pies and wine.
Well done. And are you going to leave a carrot for the reindeer?
Yeah, yes.
Well done.
We'll check back with Theo and Layla on Christmas Eve.
You? And what was your name, darling? Kate. And something special.
While children on their best behavior ask Santa for the toy of their dreams, my wish right now is a chance to hear one of the finest chamber choirs in England, the 16, filling a church with timeless sounds of the season.
leaving the tranquility of the English countryside behind. London offers Christmas fun
You've got to try and still learn these patterns even if they've been manipulated. So we'll try one more of these. So look at that one. That's pretty manipulated there, isn't it? But it's still an image of steak. So that's what we're trying to get our model to do, is still recognize this image as an image of steak, even though it's been manipulated a bit. Now, will this work or not? Hey, it might not, but that's all the nature of experimentation is. So play around. I would encourage you to go in the transforms documentation like we've just done, illustrations, change this one out, trivial augment wide, for another type of augmentation that you can find in here, and see what it does to some of our images randomly. I've just highlighted trivial augment because it's what the PyTorch team have used in their most recent blog post for their training recipe to train state-of-the-art vision models. It's what the PyTorch team have used in their most recent blog post for their training recipe to train state-of-the-art. Art vision models. So speaking of training models, let's move forward, and we've got to build our first model for this section. I'll see you in the next video. Welcome back. In the last video, we covered how the PyTorch team used Trivial Augment Wide, which is the latest state-of-the-art in data augmentation at the time of recording this video, to train their latest state-of-the-art computer vision models that are within Torch Vision. And we saw how easily we could apply Trivial Augment thanks to torchvision.transforms. And we'll just see one more of those in action, just to highlight what's going on. So it doesn't look like much happened to that image when we augment it, but we see this one has been moved over. We've got some black space there. This one has been rotated a little, and now we've got some black space there. But now's time for us to build our first computer vision model on our own custom dataset. So let's get started. We're going to go model 0. We're going to reuse the TinyVGG architecture, which we covered in the computer vision section. And the first experiment that we're going to do, we're going to build a baseline, which is what we do with model 0. We're going to build it without data augmentation. So rather than use Trivial Augment, which we've got up here, which is what the PyTorch team used to train their state-of-the-art computer vision models, we're going to start by training our computer vision model without without data augmentation. And then so later on, we can try one to see with data augmentation to see if it helps or doesn't. So let me just put a link in here, CNN Explainer. This is the model architecture that we covered in depth in the last section. So we're not going to go spend too much time here. All you have to know is that we're going to have an input of 64, 64, 3 into multiple different layers, such as convolutional layers, ReLU layers, max pool layers, and then we're going to have some output layer that suits the number of classes that we have. In this case, there's 10 different classes, but in our case, we have 3 different classes, one for pizza, steak, and sushi. So let's replicate the TinyVGG architecture from the CNN Explainer website. And this is going to be good practice, right? We're not going to spend too much time referencing their architecture. We're going to spend more time coding here. But of course, before we can train a model, what do we have to do? Well, let's go 7.1. We're going to create some transforms and loading data. We're going to load data for model 0. Now, we could, of course, use some of the variables that we already have loaded, but we're going to recreate them just to practice. So let's create a simple transform. And what is our whole premise of loading data for model 0? We want to get our data from the data folder, from pizza, steak, sushi, from the training and test folders, from their respective folders. We want to load these images and turn them into tensors. Now, we've done this a few times now, and one of the ways that we can do that is by creating a transform equals transforms.compose, and we're going to pass in, let's resize it. So transforms.resize. We're going to resize our images to be the same size as the TinyVGG architecture on the CNN Explainer website, 64, 64, 3. And then we're also going to pass in another transform to tensor, so that our images get resized to 64, 64, and then they get converted into tensors, and particularly these values within that tensor are going to be between 0 and 1. So there's our transform. Now we're going to load some data. If you want to pause the video here and try to load it yourself, I'd encourage you to try out option 1, loading image data using the image folder class, and then turn that dataset, that image folder dataset, into a data loader, so batchify it, so that we can use it with a PyTorch model. So give that a shot. Otherwise, let's go ahead and do that together. So 1, we're going to load and transform data. We've done this before, but let's just rehash on it what we do. So from Torch Vision, import datasets. Then we're going to create the train data simple. And I call this simple because we're going to use at first a simple transform, one with no data augmentation. And then later on for another modeling experiment, we're going to create another transform, one with data augmentation. So let's put this here, datasets, image folder. And let's go, the root equals the training directory. And then the transform is going to be what? It's going to be our simple transform that we've got above. And then we can put in test data simple here. And we're going to create datasets.image folder. And then we're going to pass in the root as the test directory. And we'll pass in the transform is going to be the simple transform again above. So we're performing the same transformation here on our training data and on our testing data. Then what's the next step we can do here? Well, we can turn the data sets into data loaders. So let's try. Try it out. First, we're going to import OS. Then from torch.utils.data, we're going to import data loader. And then we're going to set up batch size and number of workers. So let's go batch size. We're going to use a batch size of 32 for our first model. Num workers, which will be the number of, got a typo up here, classic. Number of workers, which will be the what? The number of CPU cores that we dedicate towards loading our data. So let's now create the data loaders. We're going to create train data loader simple, which will be equal to data loader. And the data set that goes in here will be train data simple. Then we can set the batch size equal to the batch size parameter that we just created, or hyperparameter that is. Recall a hyperparameter is something that you can set yourself. We would like to shuffle the training data, and we're going to set num workers equal to num workers. So in our case, how many cores does Google Colab have? Let's just run this. Find out how many num workers there are. I think there's going to be 2 CPUs. Wonderful. And then we're going to do the same thing for the test data loader. Test data loader simple. We're going to go data loader. We'll pass in the data set here, which is going to be the test data simple, and then we're going to go batch size equals batch size. We're not going to shuffle the test data set and then the num workers. We'll just set it to the same thing as we've got above. Beautiful. So I hope you gave that a shot, but now do you see how quickly we can get our data loaded if it's in the right format? I know we spent a lot of time going through all of these steps over multiple videos and writing lots of code, but this is how quickly we can get set up to load our data. We create a simple transform, and then we load in and transform our data at the same time, and then we turn the datasets into data loaders just like this. Now, we're ready to use these data loaders with a model. So, speaking of models, how about we build the TinyVGG architecture in the next video? And in fact, we've already done this in notebook number 3. So if you want to refer back to the model that we built there, right down here, which was model number 2, if you want to refer back to this section and give it a go yourself, I'd encourage you to do so. Otherwise, we'll build the TinyVGG architecture in the next video. Welcome back. In the last video, we got set up, starting to get ready to model our first custom dataset. And I issued you the challenge to try and replicate the TinyVGG architecture from the CNN Explainer website, which we covered in notebook number 3. But now, let's see how fast we can do that together, hey? I'm going to write down here, section 7.2. And I know we've already coded this up before, but it's good practice to see what it's like to build PyTorch models from scratch. Create TinyVGG model class. So the model is going to come from here. Previously, we created our model. There would have been one big change from the model that we created in section number 3, which is that our model in section number 3 used black and white images. But now the images that we have are going to be color images. So there's going to be 3 color channels rather tn 1. And there might be a little bit of a trick that we have to do to find out the shape later on in the classifier layer. But let's get started. We've got class TinyVGG. We're going to inherit from nn.module. This is going to be the model architecture, copying TinyVGG from CNN Explainer. And remember that it's quite a common practice in machine learning to find a model that works for a problem similar to yours and then copy it and try it on your own problem. So I only want 2 underscores there. We're going to initialize our class. We're going to give it an input shape, which will be an int. We're going to say how many hidden units do we want, which will also be an int. And we're going to have an output shape, which will be an int as well. And it's going to return something none. I'll type none. And if we go down here, we can initialize it with super._init. Beautiful. Now let's create the first conv block. So conv block 1, which recall will be this section of layers here. So conv block 1, let's do an nn.sequential to do so. Now we need conv relu max pool. So let's try this out. And then conv 2d. The in channels is going to be the input shape of our model, the input shape parameter. The out channels is going to be the number of hidden units we have, which is from, oh, I might just put enter down here. Input shape, hidden units. We're just getting those 2 there. Let's set the kernel size to 3, which will be how big the convolving window will be over our image data. There's a stride of 1 and the padding equals 1 as well. So these are the similar parameters to what the CNN Explainer website uses. And we're going to go nn relu, and then we're going to go nn conv 2d. And I want to stress that even if someone else uses like certain values for these, you don't have to copy them exactly. So just keep that in mind. You can try out various values of these. These are all hyperparameters that you can set yourself. Hidden units, out channels equals hidden units as well. Then we're going to go kernel size equals 3, stride equals 1, and we're going to put padding equals 1 as well. Then we're going to have another ReLU layer, and I believe I've forgotten a comma up here. Another ReLU layer here, and we're going to finish it off with nn.maxpool 2D, and we're going to put in the kernel size equals 2, and the stride here equals 2. Wonderful. So, oh, by the way, for maxpool 2D, the default stride value is same as the kernel size. So let's have a go here. What can we do now? Well, we could just replicate this block as block. So let's have a go here. What can we do now? Well, we could just replicate this block as block 2. So how about we copy this down here? We've already had enough practice writing this sort of code. So we're going to go conv block 2, but we need to change the input shape here. The input shape of this block. We've already had enough practice. Make this block as block 2. So how about we copy this down here? We've already had enough practice writing this sort of code. So we're going to go conv block 2, but we need to change the input shape here. The input shape of this block 2 is going to receive the output shape here. So we need to line those up. This is going to be hidden units. Hidden units. And I believe that's all we need to change there. Beautiful. So let's create the classifier layer. And the classifier layer, recall, is going to be this output layer here. So we need at some point to add a linear layer that's going to have a number of outputs equal to the number of classes that we're working with. And in this case, the number of classes is 10. But in our case, our custom data set, we have 3 classes: pizza, steak, sushi. So let's create a classifier layer, which will be nn sequential. And then we're going to pass in nn.flatten to turn the outputs of our convolutional blocks into a feature vector. And then we're going to have nn.linear. And the in features, do you remember my trick for calculating the shape for in features? I'm going to put hidden units here for the time being. Out features is going to be output shape. So I put hidden units here for the time being because we don't quite yet know what the output shape of all of these operations is going to be. Of course, we could calculate them by hand by looking up the formula for input and output shapes of convolutional layers. So the input and output shapes are here, but I prefer to just do it programmatically and let the errors tell me where I'm wrong. So we can do that by doing a forward pass. And speaking of a forward pass, let's create a forward method, because every time we have to subclass nn.module, we have to override the forward method. We've done this a few times, but as you can see, I'm picking up the pace a little bit because you've got this. So let's pass in the conv block 1. We're going to go x, then we're going to print out x.shape, and then we're going to reassign x to be self.conv block 2. So we're passing it through our second block of convolutional layers, print x.shape to check the shape here. Now this is where our model will probably error. Is because the input shape here isn't going to line up in features hidden units because we've passed all of the output of what's going through conv block 1, conv block 2 to a flatten layer because we want a feature vector to go into our nn.linear layer, our output layer, which has an out features size of output shape. And then we're going to return x. So I'm going to print x.shape here. And I just want to let you in on one little secret as well. We haven't covered this before, but we could rewrite this entire forward method, this entire stack of code, by going return self.classifier, and then going from the outside in. So we could pass in conv block 2 here, conv block 2, and then self conv block 1, and then x on the inside. So that is essentially the exact same thing as what we've done here, except this is going to benefits from operator fusion. Now, this topic is beyond the scope of this course. Essentially, all you need to know is that operator fusion behind the scenes speeds up how your GPU performs computations. So all of these are going to happen in one step. Rather than here, we are reassigning x every time we make a computation through these layers. So we're spending time going from computation back to memory, computation back to memory, whereas this kind of just chunks it all together in one hit. If you'd like to read more about this, I'd encourage you to look up the blog post, how to make your GPUs go burr from first principles. And burr means fast. That's why I love this post, right? Because it's half satire, half legitimately like GPU computer science. So if you go in here, yeah, here's what we want to avoid. We want to avoid all of this transportation between memory and compute. And then if we look in here, we might have operator fusion. There we go. This is operator fusion, the most important optimization in deep learning compilers. So I will link this, Making Deep Learning Go Burr from First Principles by Horace Hare, a great blog post that I really like, right here. So if you'd like to read more on that, it's also going to be in the extracurricular section of the course, so don't worry, it'll be there. Now, we've got a model. Oh, where did we forget a comma? Right here, of course we did. And we've got another comma up here. Did you notice these? Beautiful. Okay. So, where did we forget a comma? Right here, of course we did. And where do we... Here, a great blog post. Of course, so don't worry. Now, we've got a model. Oh, where did we forget a comma? Right here, of course. Or an instance of the tiny VGG to see out 64, the lengths, which is of course CUDA. Beautiful. So that took a few seconds, as you saw there, to move to the GPU memory. So that's just something to keep in mind